Hi, welcome back. Today we are looking at compound inequalities. Yesterday you should have watched the video about simple inequalities and what their graphs look like and how to solve them. So the only difference today is instead of looking at just a single inequality, we're going to be looking at two or more inequalities that are combined with a conjunction, just like a compound sentence in an English class is combined with a conjunction. She went to the store and she went to the gas station. Compound inequalities are the same idea. So in math, when you use the phrase and, or the word and, it means that both of those things must be true to be a solution. Whereas if we use the word or, it means only one of them needs to be true. Now, they might both be true, but only one of them needs to be true to be a solution. For example, let's say that people who are over 65 years or under 3 years old are free. So the solutions to this, or the people who qualify for the free, are anyone who's over 65. And so if I've got 0 years down here and 3 years, and let's just say I keep on going, and somewhere up here I have 65 years. Anyone who's older than 65, so 67, 68, 69, and so on, but not actually equal to 65, so I'm going to use an open circle there, or anyone who's under 3. So younger than 3, obviously we can't have negative ages, so we would have to stop at 0. However, technically, according to this statement, we would keep going forever if there was no context involved here. So a number like 70 would make this true because it satisfies the first part of my inequality. A number like 1 would make this true because it satisfies the second part of the inequality. A number like 20 would not satisfy either part of this, so it's not part of my solution. So an or statement only needs to satisfy one part of it. For example, let's say I said people who have blue eyes or brown hair don't have to do any homework tonight. There are going to be some people who have both blue eyes and brown hair. However, because they had at least one of these conditions, they qualify. So again, or does not mean that you can't have both. It just means you only need to have one. And on the other hand means that both parts need to be true. So in this scenario, people who are older than 7 and younger than 16 are allowed at a specific club. If I go and number my number line here, and this time I'm actually using consistent intervals, so 16 would be somewhere around here. I need to be older than 7, so that means anyone down this way, including, notice, 30 years old would make this part true. But I also have to be a number that's smaller than 16. So I'm looking at only numbers that fall into this range. And here, notice a number like 2 would satisfy this part of it because 2 is smaller than 16. But again, I have to make both parts true. So even though each inequality by itself would end up encompassing the entire number line if joined with an or, then I'd have every single number qualifies. The fact that there's an and between them means only when they're both true. So 7 does not fit part of my solution because it's not bigger than 7. But as soon as I get to the right of 7, I have solutions. And I have solutions all the way up to, but not including, age 16. So this idea of and means that they have to both be true, or in other words, where they overlap, where they are connected. That is where my solutions are. Another way to phrase this, notice, is if your two inequalities are pointing in opposite directions and we're finding their overlap, we essentially end up with all the values that are between two different endpoints. And when we use this between notation, we're going to start by stating the smallest endpoint. And since it's the smallest thing, we're going to have it on the small side of an inequality. Then we have all of our values that we want to include, and so that's what our variable's representing. and they are going to be smaller than the largest endpoint. So we've got essentially a between notation where we start with our smallest endpoint, stating it. We state our largest endpoint. We say x is between those two things. And this notation can only be used for an and statement. Because if it was an or statement, saying that I'm bigger than my smallest number, or I'm smaller than my largest number, if I use the word or, I would have every value on the number line included here. This has to be an and because we want to stop when I get beyond the largest endpoint. I have to stay smaller than 16. So not only do I have to be bigger than 7, but I also have to stay smaller than 16. And so whenever you use this notation, we mean and. All right, let's go on to how to solve these. Essentially, you are solving compound inequalities exactly like you solved simple inequalities. In this scenario, we have a single inequality and another simple inequality and the word or between them. So we would simply solve or graph each piece of it, and then we would find, in this case, all the points that make one of them or the other or both true. In this scenario, we're looking for when they are both true. So we just go to our number line, start placing some numbers on here, equally spaced, 2, 4, 6. We start by saying x has to be greater than 4, so I'm using an open circle at 4 to not include it. And I want all the numbers bigger than 4. Notice 5 is a solution to this. 5 is greater than 4. Then I also want to include all the numbers that are smaller than -1. So again, an open circle at -1. And I want to pick numbers that are smaller, like -2 would be a solution to this inequality. So it would be shaded. Because the word or is being used, that means that they don't have to overlap. This solution shows me all the numbers that would satisfy one or both parts of my inequality. So this is my graph. Same idea here, except now I'm going to use and. So if this is -2, 0, 2, 4, which means 3 is here. I want to be smaller than 3, so I'm going to go this way from 3, and I need to be greater than or equal to -2. So I'm only going where they overlap, and notice that since this shading will continue this way, they will both be true at -2. That will satisfy both inequalities, and they will both be true in this span here all the way up to, but not including, because notice my bottom one's not true at 3, all the way up to but not including 3. So what I have here in that middle section in red, that is the solution graph of this compound inequality. I wouldn't leave the separate pieces there. I want to make sure that I'm showing only numbers that are smaller than 3 and at the same time greater than or equal to -2. If I come down here at -4, while -4 makes this part true, it does not make that part true, so it's not part of my solutions. If I come up here and pick a number like 5, 5 makes this, this part true. 5 is greater than or equal to -2, but it does not make this part true. 5 is not less than 3. But any number in this span here will make them both true. When you see this between notation, you can typically assume that you're going to shade from small number to big number, but just make sure that it's not written in an awkward way. Look at the two separate pieces. This one right here says x has to be greater than -4. So if I start at -4, I want to stay greater than -4. And the other part of my inequality says that x has to be less than or equal to 2. And so if I continue on to 2, I'm going to go equal and less than. And so sure enough, using that idea that this means and, I don't want to go beyond either one of these endpoints, I will be shading between -4 at the small end and 2 at the large end. All right, last piece is how to solve these. And you solve them just like we solved with simple inequalities. In this case, I have a single inequality where I have a coefficient to eliminate. Dividing by 3 gets me that x is smaller than 8. Over here, I'm dividing by -2. Keep in mind that when we divide by a negative or we multiply by a negative, the inequality relationship gets changed. So the negative side became positive, the positive side became negative, and therefore the relationship large to small also changed. Make sure you write the word and back in between them because that's what joins these to make one solution. And then we come down and we graph those values. So -2 is one of our endpoints, and I want x to stay larger than -2. So that means this side. My other endpoint is at 8, and I need to stay smaller than 8. So I'm going to have another endpoint here, and I want to be smaller than 8. And because the word and is being used, I know that I can't go beyond either one of those endpoints. If I check any value that's not shaded, it's going to make at least one of these two inequality statements false. So notice here I get 30 is less than 24. That's false. So I know that that's not part of my solution. Checking a value over here like -4. -4 makes this side work because I'll get -12 is less than 24. But when I check -4 here, I'll get 8 is less than 4, and that's not true. So it doesn't work either. My endpoints themselves should satisfy the equation, one or the other equation, and all the points in between should satisfy the inequality, making both this side and this side true. When you see a problem with a between notation, remember that this is really two inequalities. You've got this inequality here that says 5 is less than 2x plus 6, but you've also got this part here that says 2x plus 6 is also going to be less than or equal to 14. So we could pull it apart, taking the stuff in the middle and solving the inequality where that stuff is less than or equal to 14, and solving the inequality where that stuff is greater than 5. Solving each one of these separately will involve the exact same steps. I'm going to subtract 6, and I'm going to divide by 2. So rather than doing them separately, we're going to do them all at the same time by simply drawing in two lines, one at each inequality. And whatever I do in here to isolate this value of x, I'm going to do on both sides of this inequality, and I'm going to do on both sides of this inequality. So I'm solving them simultaneously. The first thing I do is get rid of my 6. So when I do that, I do it on both sides of this inequality, and I also do it on both sides of this inequality. Every piece of this relationship will get 6 smaller. So the smallest part stays smallest, and the largest part stays largest, because everything goes down by the same amount. The next thing I'm going to do is divide by that coefficient, and again, in order to keep the relationship, I need to make sure I do it in all parts of this relationship. When this gets cut in half, this also has to get cut in half, and this right here also has to get cut in half. Now that I've gotten x by itself, I can see that x has to be greater than -1/2, but at the same time, x has to be smaller than or equal to 4. And so if I go to graph this on my number line, -1, -2, this will be 1, 2, 3, 4. I start with x being smaller than or equal to 4. So that's this way. And x has to be greater than -1/2, which is going to be right here. Now, because there's no label on it yet, I do need to include a label there telling what this endpoint is, whereas 4 was already labeled. So x is greater than -1/2, and because x is written between them, I know that this is one where both parts have to be true, so I can't go beyond either endpoint. My last one down here, I have an or statement. Just like with my and statement that I did up there, I'm just solving two separate inequalities. In this case, I'm trying to get x by itself, so I'm going to add 3 to each side and get that x is greater than or equal to 10. Then I have my word or again, because I still need to have my solutions combined. I'm going to subtract 5 from each side. Notice that leaves me with a -2x is greater than -8. And then I'm going to divide by -2, remembering that if I divide or multiply by a negative, that inequality relationship changes. So my negative side became positive, this side negative becomes positive, and the relationship of greater than less than reverses. So my solution in this problem is all numbers x that are greater than or equal to 10, or those numbers have to be smaller than 4. And when I come down and graph the solution, again, I'm going to put some numbers on a number line here, 4, 6, 8, 10, 12. And I want numbers that are smaller than 4. So open circle here, shade to the left. Or my numbers have to be greater than or equal to 10. So filled in circle, shaded to the right. As long as the number's in one of these two shaded regions, it will satisfy my inequality. You can come back and test this. If I put 0 in up here, I get -3 is greater than or equal to 7. That's false. But only one of these two parts needs to be true. If I put in 0 over here, I get 5 is greater than -3, and that's the true part of this statement. So again, any number that's shaded is going to make at least one of these two parts true. Any number that's not shaded will make both of them false. So hopefully you feel like you've got a better idea of how to solve and